Hello, I'm Justin Rutledge, and I'm here to describe the implementation and execution results of a program that fulfills the criteria of Homework Assignment 1 for CPSC 5260 at the University of Tennessee, Chattanooga. So I'll start by describing what the program's intent is, the main method of the program, its supporting functions, and then finally the execution results. So this program generates a random array and shows that standard deviation lowers of all the elements in that array as the array is smoothed over time. So at first I get 4 values from the user. One is the size of the array. The next value is the scale value, which is used as a factor with the random number generator so that we're not stuck with a value between 0 and 1. Next we get a double between 0 and 1, that's the smooth weight that's applied to the formula during each smoothing iteration. And then lastly, we get an integer from the user that's the number of iterations of smoothing that is desired to be performed. Next, we'll allocate memory for the array, and here I multiply the size of the array times 8 because a double takes up 8 bytes in memory. I'll initialize the array with random values and let the user know that it's about to perform X iterations of the smoothing operation, however many the user had selected earlier, and then show the standard deviation each time. This is the core of the main method here. For essentially 0 through however many iterations the user is defined, it will print the iteration number that it's on, the standard deviation of the array as it currently is, and then it will smooth the array and then start again. This smoothing operation happens for all cases except for the last one, and it just doesn't happen on the last one because it doesn't make any sense for it to, since it won't be used for anything. Lastly, the user gets some feedback showing that the program is complete, and then I've just put in here a quick and easy way to clear the inputs and allow the user to just press the enter key to exit the program. This will allow us to see our results without the command prompt or the terminal closing on its own. Okay, so let's go into some of these supporting functions. We'll start with the random array, and so this function takes in an array from memory, takes in the address of an array in memory, and then operates on it with a for loop that iterates from 0 to the size of the array, and then essentially for each element in the array, it's going to set it to a random value. And this random value uses the standard C library's rand function, which requires us to seed it, and I've chosen to seed it with the current system clock time. So each time this program is run, it's going to have a different value. And that random number is divided by the constant that's associated with the standard C library for the max random value, divided by the scale. And we'll see this produces essentially any number between 0 and whatever the user had entered as the scale value. Lastly, we print each value as it's generated for the array so that the user can see what's going on and give them feedback that it was successfully populated. Okay, so now that we've created our random array, we can then start iterating on it. And we get the standard deviation, then we smooth, then we get the standard deviation, then we smooth. So let's look at standard deviation for a second. So here's the standard deviation function. And what this function does is essentially implement the standard formula for standard deviation, which I've written right here, where you get the square root of the sum of x minus u at their absolute value squared divided by n, where u is the mean value of all values in the array, x is each element value as we iterate, and then n is the size of the array. So we start by calculating the mean, right? I've broken down this formula into several parts. We'll start by calculating the mean, which here is u, right? We need to get that. We'll put it in a variable called mean. And next, we get the next thing I do is allocate memory for a new array, and I call it the diff squared array. So this is basically finding the difference between the current element and the mean squared. The absolute value here, it's worth noting, doesn't really matter since we're dealing with all positive values based on how we've set up this program. So I've even included that here. Where we would want to get the absolute value, it's not necessary. So for each value in the array, we take the difference of that value and the mean, and then we square it. And that's fulfilling this portion of the formula here. and then we set the new arrays, what I call the div squared arrays, current value equal to that value. So we do that over the course of the whole array, and then we'll sum up all the values of the new array by using the function sum, which is another one of the supporting functions I've implemented. And it's really simple. It just iterates from 0 to the size of the array and adds the value of each element to the sum. It's pretty straightforward. Okay, we come back to the let's come back to the standard deviation function. All right, so we get the sum of that different squared array. All right, and so if we go back to this formula here, we fulfilled this step. Now we divide by the size of the array, right, which is right here, and then we return the square root of that value, and that fulfills this function in its entirety. It's just broken down into bits that are easier to read. Okay. The next supporting function is the smooth function. So every time that we find the standard deviation, we're also going to smooth the array and then go back to find the standard deviation again. And Dr. Liang had provided a formula for this in the assignment, and it's right here. And this is just an implementation of that formula using W as the weight that the user has described in the initial prompts for the program. So from I equals 1, because we are not wanting to change the first or last value, from I equals 1 to I size minus 1, right? We're not changing the furthest left or the furthest right value. We iterate through the whole array and then set the current value of the array equal to the formula. Now note here I've set up a couple of temporary values, one called old value and one called temp. Old value is initialized to the first value in the array, and then each time old value is set to whatever the current value of the array is before it's changed, and then that old value is used in the change operation right here. Okay, that finishes it up for the implementation part. Now we will take a look at the execution results. Okay, so I've pulled up a new screen capture here now to show in PowerShell instead of the IDE what the execution results are. So let's start by compiling the program. So we compile HW1.c and set the output file to HW1.exe. And let's do that again, but set the -wall flag to show that there are no compiler errors. Okay, and now let's run the program. All right, so first we set the size of the array, and we're supposed to have a small-ish array, so let's say we have 20 elements in the array. Now we'll set the scale value of the randomized array, so let's set that to 9,999 so that we have a wide range of values to work with. We'll set the smoothing weight to something pretty small, like 0.1. And finally, let's smooth it 10 times, and let's see what we get. Okay, very good. So as we see here, each element of the array has been assigned a random number between 0 and 9,999. It was successfully populated for all 20 elements. We performed then 10 iterations of the smoothing operation, and we'll show the standard deviation each time. And here we can see after iteration, or for iteration 1, what the standard deviation is at the beginning before any smoothing operation is applied is over 3,000. The second iteration is just over 2,000, 1,700, 1,500, and so on and so forth. And we can clearly see that this value, the standard deviation, reduces over time. It looks like it's converging on an asymptote somewhere around 1,343 for this particular array with this particular smoothing weight. So I'd imagine if we continued to run iterations, it would stay somewhere around 1,340, and it wouldn't reduce dramatically much further than that. The array has been pretty closely smoothed at this point, it seems. Anyways, that's it for the execution results, and I believe this concludes the assignment. Thank you.